Fabricio Toscano. He is an associate professor of physics at Institute of Physics, Federal University of Rio de Janeiro in Brazil, in the quantum optics and quantum information group. His research interest lies in the areas of quantum information, quantum mechanics, open systems and decoherence, quantum to classical transition, quantum chaos, semi-classical mechanics. So today, Professor Toscano is going to talk on optimal quantum teleportation protocols for fixed average fidelity. Over to Professor Toscano.
Thank you very much for the introduction. Good evening to everybody. You are hearing me well?
Yes, we can hear you well.
Okay. Let me Did you see the presentation or not?
No, it's coming. I think hasn't come yet.
No, I cannot also see.
No, it's not coming. Yeah.
Let me.
Yeah, now it is there. So you can, yeah.
Okay. First, let me introduce my collaborators in this work that we have Diego Busardri for the Instituto of La Plata in Argentina, Professor Gustavo Bosic from the same institute, Ana Magtey, professor at the University of Córdoba, Argentina, Professor Mariela Portesi from the Institute in La Plata, Argentina. I'm going to talk about a subject that was introduced 30 years ago, the first proposal of quantum teleportation of qubits. And a lot of work has been done on this subject, but we think that we have something new to say about this. Let's start. Remember which are a general quantum teleportation protocol for a qubit. You have two parties, Alice and Bob. Alice has a qubit system, and this qubit system was prepared in an unknown pure state to her, and Alice wants to transmit this state to the qubit system of Bob. In order to do that, they share a two qubit state between an auxiliary qubit system in the Alice size, and these two qubits here are in a general two qubit system, two qubit state that it is called the resource state. And after a general POVM on these two qubits performed by Alice, the state of the qubit at Bob's side is collapsed to some state, and after a classical communication of the result M of Alice, Bob performs a unitary operation that is a rotation of his qubit. So the general protocol is characterized by one resource state, a POVM, and a rotation in the both sides. Sorry. Sorry about that. The performance of the protocol is evaluated by a quantity that is the average fidelity. This fidelity is defined as average over all the results, the final states that appears here in the both side, and also average over all Q states in the Bloch sphere of Alice. It's easy to realize that several protocols come to the same value of the average fidelity. So a question that appears immediately is which of those protocols are the optimal protocols? Okay, so this is the question that we are giving an answer here. Okay, so to answer this question, first let's look how to describe the ingredients of a general quantum teleportation protocol. First, we have the resource state that in the Fano form is described by two Bloch vectors of the marginal states of these two qubit states, and a correlation matrix here. And the POVM, the elements of the POVM, also can be described by each element can be described by two qubits, two qubit states that in the final form also are characterized by Bloch vectors and a correlation matrix. Okay, so these are the ingredients to describe the protocol. Okay, of course, the elements of the POVM must be connected through this POVM condition that establish conditions on these Bloch vectors and this correlation matrix. Okay, here. Okay. So also the protocols can be described with Bloch vectors in the Bloch sphere, and here we have the Bloch vector of the Bob state after Alice measurement that is connected with the Bloch vector of the initial state. And these quantities here that appears here and here, this is an affine transformation that we have here a matrix, and this is a vector. And these matrices and this vector are constructed with the ingredients that I talked before. These are the resource state, and these are the POVM elements. Okay. So after the communication of M, Bob performs a rotation. Okay. So to each protocol or general protocol described by these Bloch vectors can be constructed and a quantum teleportation channel that is the average of the results of the states in the both sides. And the Bloch vector associated with this channel is this. And we have a matrix that is that characterizes the quantum channel, and a vector, that the affine vector of the channel. And with these two ingredients, we can calculate the average fidelity and the fidelity deviation, that is the dispersion of the fidelities around this mean value here. And we see immediately that several protocols can be constructed with the same matrix C, and we want to answer which are the optimal ones, okay? But it's important to realize that all these protocols that gives the same average fidelity are not physically equivalent, because the output state can be very, very distinct, okay? So to answer this question, we make use of another distance, okay, that gives measure how well the output state is with respect to the input state. And this is the trace distance that in the Bloch sphere are given by this expression here of the Bloch vectors of the initial state and the output state. And we are looking on the average trace distance. If there is any question?
No, sorry, somebody's microphone was on. Please continue.
Okay. So we have here the average trace distance, and we want to lower bound this expression, and let's start doing that. First, we use the Jensen inequality that is applied to any norm. Any norm is a convex function, okay? So we see that this sum here enters in this expression here, and we recover here the Bloch vector of the teleportation channel. So this is the trace distance between the initial state and the Bloch vector or the state of associated with the channel. And it is always true that the trace distance is lower bounded by 1 minus the fidelity between these two states. This is the expression. And it is relatively easy to work out this expression to calculate in terms of the matrix that characterizes the channel. And this is the expression. And as we already see, the average fidelity of the protocol can also be related with this trace here, and the relation is here, okay? So we have the average fidelity of, if we fix this average fidelity, there are many protocols which whose average trace distance is greater than this quantity here, but we see that we can saturate these inequalities here both of them, if and only if the Bloch vector of the final state after Alice measurement is aligned with the initial Bloch vector of the initial state, pure state in the Alice side. But this factor here is connected with the fidelity to this expression here. Okay. So we see that between all the protocols with the same average fidelity, those with that the Bloch vector, the final Bloch vector, is aligned with the initial Bloch vector. This means that the final state is diagonal in the same basis as the initial one. Has the minimum average trace distance. Okay, so we call this type of protocols, the protocols that align, okay, the optimal protocols. So now let's see how we can characterize these protocols. Okay. So in order to characterize these protocols, we demonstrate two theorems. The first one is this one here, and said that an arbitrary quantum teleportation protocol aligns if and only if these three conditions are verified. The first one, cancel this term here. This one cancel these two terms here, and this one cancel these two terms here. The demonstration of this theorem make use the POVM conditions that relates the Bloch vector of the marginal state of the POVM elements and the correlation matrix of the POVM elements. And we see that after these conditions are applied, it survives only this here. So this matrix here, because this is a rotation, this matrix here must be an orthogonal rotation matrix. Okay? So this is the first condition to a protocol, to a general protocol, align the final Bloch vector. Okay. It is very easy to calculate the matrix that characterize the channel associated with these protocols, and is proportional to the identity, and this vector is 0. So the average fidelity is 0. Okay. So all the protocols that are optimal, okay, has 0 fidelity deviation. Okay. This is a nice property. So let's see the condition that appears in this theorem. First one is that the Bloch vector of the Martian state of the resource state on the both sides is 0. So the marginal state on this side is proportional to the identity. The same happens for the POVM elements in the qubit A, in the Alice side, that the Bloch vector is 0. But the Bloch vectors of the marginal state corresponding to the qubit A bar on the Alice side is connected with the Bloch vector of the marginal state in the resource state by this relation here. This is the correlation matrix of the POVM elements. Okay. So the second theorem that characterizes all the protocols that are aligned is this one. First, the correlation matrices can be written of the PVM state, and the resource state can be written in this way. These matrices that appear here are the matrices that brings this resource state and this POVM element to the canonical form. So these are the matrices that diagonalize these matrices here. And these are diagonal matrices here. This is the diagonal matrix that characterizes the resource state, and the diagonal matrix that characterizes the POVM elements are connected to this matrix here. Okay. The next condition is that this matrix here must be fulfill the PVM condition, that is this one here. And the last condition is that the rotation matrix that is, we have seen that is given with this expression here, and we substitute this in this with this, we obtain the product of these two matrices. This is the matrix that brings the POVM element to the canonical form, and this is the matrix that brings the resource state to the canonical form. Okay. So these are the conditions that must be satisfied for every protocol that is optimal. Okay. This means that the average trace distance is minimum for an average fidelity fixed, and in that case the final block vector is aligned with the initial block vector, and all this condition depends essentially on the diagonal elements of the matrix of the resource state that is connected with this matrix here, and also through this connection here. Okay. But the values of these matrix elements and the value of these vectors here cannot be arbitrary. It must be, it must fulfill the condition that gives a density operator, density operators, resource state POVM elements that are physical. And there is a nice set of inequalities that Gamel in 2016 gives in this paper here, that in the case when this marginal block vector is 0 and the determinant of the correlation matrix of the resource state is different from 0, we see that this is a requirement because this is a rotation matrix, right? And depends on this matrix here. So there are only two inequalities that this matrix and this state here must fulfill, that are these two inequalities here. Okay, this one and this one. Of course, that the correlation matrix of the POVM elements and the block vectors of the POVM elements must fulfill also the same inequalities. So there are a set of 4 inequalities that has to fulfill. To give an idea how this inequality it means, let's look, for example, when in the resource state, okay, in the resource state, both marginal block vectors are 0. So this means that this state here is a Bell diagonal state. And in that case, this inequality is trivially verified So the only inequality that gives a restriction is the lower bound, and this is 0 because of this. And this inequality gives the very well-known tetrahedron in where these x's here are the diagonal elements of this matrix here. Okay. In our case, where we have to fulfill 4 inequalities, remember that the correlation matrix of the P of M elements are related with the correlation matrix of the resource states. And so we can plot the intersection of these 4 inequalities. And here we plot, for example, when this is the case, these two are the cases where the Bloch vector of the marginal state of the resource state is 0. So we see that these sets that are in red here are the intersection of, so the allowed correlation matrix, this correlation matrix that for all the protocols that align for this given, this essentially S equal this number here gives essentially the average fidelity. So for this average fidelity, these are all the protocols that align. And you see that when this factor here S go to 1, these sets goes to a point that are the bell states. Okay, so our theorem shows that the only optimal protocol with fidelity equal to 1 is the very well-known perfect teleportation protocol that are constructed with the Bell states, and the P of M is a Bell measurement. Okay. So let's look for a moment again on this condition here. That is the composition of the correlation matrix of the P of M elements. And we see that this matrix, as we have said, are related with the local unitaries that you need to apply to obtain a canonical form of the two mode or two qubit system here. Okay, the canonical form is that state that through local unitary operations you bring the correlation matrix in a diagonal form. Okay, but if you do that for the resource state and for the P of M elements, you see that this matrix here, or that means that this unitary operation here and here are the same. So if you put this and this here, this unitary operation does not appear here. So the final state does not depend on this unitary operation. Okay, so we can skip this matrix here. Okay, this matrix here doesn't give any new information. So let us look now a subset of protocols that are optimal, but with this matrix here that are associated with a local unity operation that brings to the canonical form that are diagonal. Okay, we want that this matrix here is diagonal. Okay, but in that case, it's easy to see that in order to fulfill this condition here, we see that this matrix appears here, but if this matrix is diagonal, the only way to fulfill this is where these matrices here are diagonal also, and the only matrix that are rotation are diagonal are these four matrices here, and the condition is that if you put this matrix here, this S here is easy to realize that must be equal for all M. This means that this kind of protocols that we call the deterministic quantum teleportation protocols that align, meaning that they are optimal, are unconditional, okay? Because to any result of Alice measurement, this parameter here, that is essentially the average fidelity, is the same, okay? Well, for this kind of protocols, we can associate a noisy channel, okay? Let me explain what I mean. So the correlation matrix for this kind of protocols are of this form. This is a diagonal matrix, and the correlation matrix of the POVM state are diagonal because this matrix here is diagonal, and this we impose that this is diagonal. So for this kind of protocols, okay, that we see that the rotation matrix that Bob have to apply is given by this matrix here, where this is diagonal, and these protocols are optimal. When this is 1, the fidelity is 1, so the average fidelity is 0, okay? And this is the perfect quantum teleportation protocol, but we prove that the canonical form of the POVM states and the resource states that are here for this kind of protocols can be seen as a noisy channel that is applied on the Alice qubit, both in the resource state and in the POVM states. But this condition here imposes that in general, these noisy channels are correlated. So these noisy channels are applied to the perfect quantum teleportation protocol, okay? So the teleportation protocols that align for a fidelity that is not 1, okay, for a fidelity that is not 1, can be seen as the application of noisy channels in the Alice qubits to the perfect quantum teleportation protocols, okay? But in general, these two channels are correlated because of this condition here. So let's look more closely on these channels. We remember here that a qubit channel in general in the canonical form of the qubit channel is described by a diagonal matrix and a vector, that is the translation vector of the channel. So in the case in this theorem here, this matrix of this channel here on the resource state is given by this two product of the two diagonal matrices. One is the diagonal matrix of the resource state, and this is the diagonal matrix associated with this Bell state. In this case, the affine vector here is 0, and for this channel, the matrix that characterizes the channel is proportional to the inverse of this matrix here. Okay, and the affine vector, because of this condition here, are also connected with the Bloch vector of the marginal state of this state in the qubit A. Okay. So in the particular case where we consider unital qubit channels, where this affine vector is 0, okay, we see that this is 0, meaning that this is 0, so this condition is no longer applied. So in this case, we see, and if we impose that this matrix, these two matrices that characterize these two noisy channels are equal, this means that these two channels are not more correlated, are the same type of noise in the 2 qubits of Alice. And this condition here, because of this, it is easy to see that the channel is a depolarizing channel. Okay. So for every, because of the average fidelity is connected with this parameter S here through this simple expression, it is easy to realize that for every fidelity, you have a channel, the polarizing channel that correspond to describe the protocol as a depolarizing channel on the perfect protocol. Okay. So let's look, for example, here, which type of resource states and POVM elements appears when you have a depolarizing channels on Alice qubits. And this kind of protocols is the intersection of these lines that are blue with the allowed protocols here, or here for another, this is for one fidelity and for another fidelity. And this line here correspond to Wegener states, okay? That is the action of the noisy channels, the polarizable noisy channels on the perfect protocol, okay? But there are a lot of protocols that align, that are optimal, corresponding to the polarizing channels, but the polarizing channels can be correlated. They are not correlated only to these points here that correspond to this case here. Okay, in that case, the polarizing channels are not correlated. Okay, so let's come to the conclusions. Okay, I don't know if is very quickly the presentation, but we have more time to discuss. So the two main things that I want to point out here is that for every average fidelity, the optimal qubits quantum teleportation protocols correspond to those such the input and output state are diagonal in the same basis. This means that the Bloch vectors are aligned because they exhibit the minimum average trace distance. Okay, and the second that I want to point out here is that if Alice and Bob try to prepare the perfect quantum teleportation protocol, this is the case where the POVM states are Bell states and the POVM elements are Bell measurements. But Alice, in the Alice qubits, exhibit the polarizing noise that is the most very common case in experimental setups. Still, the protocol is optimal, but with an average fidelity that is less than 1. So these are one of the more important message of this work. So I want to thank you very much for the invitation to deliver this talk, to your attention. And finally, I want to present the group here in Rio de Janeiro. We are 7 professors in theoreticians, and we have a laboratory that is optical quantum optics laboratory, where the main experimental setup is the parametric down conversion of photons. And these are the 2 professors. And all of you are welcome to come and visit us here. Okay, so.
Yeah, thank you, Professor Toscano, for a wonderful talk. It was very understandable. And thank you for inviting all of us to Rio de Janeiro. It's a fantastic place, I know. So there is open for questioning. If there are any questions, please unmute and ask.
Hello, sir. I have a question.
Yeah, Raju, then go ahead.
Sir, actually, you talked about correlated depolarizing channel. So, is the correlations like it is a special correlation or time correlation?
He's asking, is it spatial correlation or time correlation? Yeah.
Spatial. No, you are talking about the polarizing channel.
Yes. Correlated depolarizing channel. What kind of correlation is that? It is spatial or time correlations?
What I mean correlation here is that let me. So you see that here these are the Bloch vector of the POVM elements. Okay, so in 1 qubit on the Alice side, and this is the Bloch vector of the resource states. And in order to align the final Bloch vector with the initial Bloch vector of the Alice qubit, this condition must be fulfilled. So this is the correlation that appear here. Okay.
Okay.
So you can translate this correlation, okay, into a correlation of the polarizing channels here, because these conditions here, all the condition that gives the protocols that align, okay, it can be seen as the action of the polarizing channels on the Alice qubits when they try to prepare the perfect quantum teleportation. But these 2 channels here are correlated, but okay, because of this condition here, right? They are not correlated when this condition is 0. This means that this vector here must be 0. Okay, so correlation, the word correlation here is related exactly with this condition here. Okay.
Okay. Thank you.
Okay, next question. Actually, it's late in the day. I think people are tired. It's almost 8 o'clock. So for
I
you,
realize that.
morning, right? So yeah, right.
Yes.
Thank you. Thank you, Professor Toscano. Thank you very much for giving
Thank
this
you very
talk.
much for the invitation.
Yeah, yeah. Thank you.
So I have a one small question.
Okay, okay.
Yeah. So
Professor Toscano? Yeah. Just one
sir,
question.
can briefly explain what is a vector marginal state again? I think when you were explaining, my network was fluctuating.
Sorry,
So she is asking, can you explain vector marginal state again? Because at that time her network had gone down. So that's why. Yeah.
So there is a way to represent the two qubit states, that is the Fano form here. And you see that appears two vectors here. Okay, this is a vector. This is a vector of the Pauli matrices. Okay, and if you calculate the trace of this operator here, density operator, for example, with relation. Okay, so the Bloch vector associated with the marginal state, maybe here you see that the Bloch vector of this marginal state here is this one. Okay, this is the marginal, the Bloch vector associated with the marginal state when you trace over the other qubit. And you have two vectors.
Thank you, sir.
When this vector is 0, the marginal state is proportional to the identity. Okay.
Okay. Thank you, Professor. Thank you once again. Good night. Yeah, or for you.
Good night.